Hi and welcome to feyn lab lectures. This is the part 2 of the rotational body motion. So we shall discuss about the relationship between the translational motion and the rotational motion today. So we know from what we have here that x is equal to r times theta. So this is the x line and this is the s, then theta, and this is the 0, and this is particle p, right? So that is the theta, and theta is equal to s by r, right? From that equation you get x is equal to r theta. So this is displacement here, and this is angular displacement. So this is displacement, linear displacement, this is angular displacement. So from this equation you get this. So again, if you differentiate it, v is equal to r omega. It can also be written as v here again is the linear velocity is equal to r times angular velocity, and t, let's look about that. T is equal to c by v, or it can also be written as 2 pi by omega. So t here is the time period. Since the body is rotating, you calculate the revolutions per minute or per second. So that's the time period. So time period here is nothing but 2 pi by w2, or circumference of the circle, or the circumference of the circular motion, the circular path traced by the body by the time, by velocity. The linear velocity gives you the correct answer. So now acceleration. So a is equal to r omega, sorry, r. Differentiate this equation again. So a is equal to r alpha. A can also be written as v squared by r omega, sorry, omega squared r omega squared, or omega squared r. All are the same, so it can be written in this form. So here a is the linear acceleration, r the radius of the circular track, alpha is the angular acceleration expressed in revolutions per second, and v squared by r is equal to s omega square, or omega square r. So these are the relationship between the linear acceleration and the linear acceleration, the rotational acceleration, or the translational acceleration, or the rotational acceleration. So next, so rotation with constant acceleration. So if the alpha is constant, then you have the equations of motion, just like in linear equations that we had for the motion under constant acceleration. In the same way we have here as well. What you've got to do is you've got to replace those v by omegas, and v is equal to u plus at that I wrote can be written as w is equal to omega naught, sorry, omega is equal to omega naught plus rt here, or omega. Again, theta minus theta naught, nothing but x is equal to ut plus half at square. So omega t plus half alpha t square, and then omega square minus omega naught square is equal to alpha t u square plus 2 apologize 2 alpha t 2as, so 2a theta 2 theta minus theta naught, right, so theta minus theta naught, because it's v squared minus u squared is equal to 2as or x. So here it is x is equal to ut plus half at squared, v equals u plus at. So this is what the equations stand for in the angular acceleration. So it's quite easy, to just substitute those equations and find out. Now, kinetic energy of rotation. So how do you write the kinetic energy of rotation? Well, same way. Since it's a rigid body, you got to find out the kinetic energy of every particle that constitutes the rigid body. And yes, kinetic energy is given by the formula sigma I is equal to 1 n half. Half can be taken out if you want, but mi vi squared. Okay, that is nothing but half m1 v1 squared plus half m2 v2 squared plus half m3 v3 squared plus half mn vn squared plus. Okay, so this is what it is. However, there is a hope for easiness in one sense, not complicatedness. Okay, so the way to not make it complicated is by introducing something called as the moment of inertia. So the moment of inertia is nothing but the mass of the rotational body distributed about its axis. So since I drew this diagram, this is a rigid body. So the mass of the rigid body distributed about its axis is called the moment of inertia. Moment of inertia given by I. So this is the axis of rotation. So the mass is distributed along the axis of rotation in a rigid body. We know that, hence that is I. Okay, so the moment of inertia is nothing but the mass distributed along the axis of rotation or around the axis of rotation. That gives you the inertia. So how do you define kinetic energy in terms of moment of inertia? So I is equal to sigma m I r I squared. Right? So that is what is the moment of inertia formula. So K is nothing but half I omega squared. So from half mv squared we arrive at half I omega squared. Okay, so rotational motion of rotating body also depends on the distribution of the mass of the body, and since the mass is distributed more or at the axis of rotation, mass is distributed closer towards the axis of rotation, the first rotation is easy. Okay, so easier the body to rotate. If the mass is well distributed along the axis of rotation, it's easy for the body to rotate. Okay, so very good. Fine. Now, what about the rotational inertia? You cannot keep finding the, if you wanted to find the center of mass instead of finding the moment of inertia, if you find out something at the center of mass, it will be zero, right? Because it's rotation and the body is moving in terms of it's an angular movement or motion. So if you try and find out the acceleration or the velocity of the center of mass and then put it in the kinetic energy, you're doomed. You get 0 as an answer. So hence you got to open up something into something called as the rotational inertia. So rotational inertia, Ri, is calculated. Of course, you cannot calculate for every individual particle in the system or in the body. So it's nothing but r square by dm. Again, dm is the mass element, differential mass element. So because the individual particles are so small compared to the mass of the system itself. So hence you can take it as the differential mass element. So I is equal to integral of r square dm. So that gives you the rotational inertia. Now for the parallel axis theorem, I'm just going to define it. I'm so sorry I cannot derive it because one, it is integration. Of course I know, but this lecture is to motivate people to take up science. So it won't be actually mathematics should most of the times is not taken into consideration, even though physics is all about mathematics most of the times. Every law can be represented with a mathematical equation, but we normally, when scientists do the lectures, we often never include equations that are complex as the integration or differentiation. So anyway, so what I'm going to do is I'm going to just define the parallel axis theorem, and as I said, I don't think it is much of importance to derive the equation. However, it's a long one. So I is equal to I COM plus mh squared. Here ICOM is the moment of inertia of the center of mass plus the total mass of the body, and h is the perpendicular distance between the given axis and the axis through the center of mass. Okay, so this is the formula for rotational inertia about an axis of rotation in other sense. So the moment of inertia about the axis of rotation is nothing but the moment of inertia about the COM, total mass, and this is the perpendicular distance between the AOR and the axis of COM. Right? So this is the parallel axis theorem. Very important theorem actually. But the difference between, relation between the parallel axis theorem and the perpendicular axis theorem is very important. However, I don't know whether I'll be doing it or not, but hopefully I might as well do. But at the same time, I mentioned that it's just a lecture. I think you can refer to introductory the concepts of physics by H.A. Verma. In that book, of course, you'll find it's the Bible for IITs. So anyway, you can get into that and practice if you want. But since I don't want, I've done twice and my teacher has taught me once, but it's over and it's over. So I don't feel it important. It is important to do. Okay, so however, let's move on to something called as torque. So torque represented by tau. So say there is a body, so any kind, but I'm just taking a circular body here. So if I apply a force in this direction, and this is the r, the radius, so torque is the product of force and radius. The property torque is the intention, the ability to rotate the body. So this is the action, line of action. This is the moment of torque. So the point here is that the torque actually is directly dependent on the force and also the distance from the center of the body. So actually, in order to open the door, you cannot push the door at the first end. Okay, you have to push the door at the other end where you have the doorknob, and you open the doorknob and then pull or push. Okay, you do either and then the door opens, but you cannot do the same thing on the other side. So well, it will take ever for one to open the door on the other side. So anyway, so that is one of the everyday experiences of torque. So torque is F times R cos theta is the formula one can use for calculating the torque. However, we will discuss in detail about the torque in the next coming lecture, the part 3 of this lecture. So for now, this is all I have for torque. Let's move on to the next topic that we have is defining Newton's laws in terms of torque. You just compare F equals ma and T equals I alpha. Sorry, torque is not A. So anyway, torque is equal to I alpha. So this is the moment of inertia. As I said, that's nothing but the mass, the distribution of mass along the axis of rotation is nothing but this moment of inertia. It's nothing but mass. And alpha is the angular acceleration, and that yields torque. In a comparison, it can be done. You can distinguish between the two equations, right? So one more interesting thing about torque, I think this is all I have about the torque to say. So torque it obeys superposition of forces. Just like we discussed in the Newton laws, Newtonian mechanics, that force obeys superposition of forces. Of course, sound does, and we shall see it in detail later. But however, Newton torque obeys the law of superposition of forces. Okay, so torque is superposed, can be superposed. Now, in the work and the energy lecture, we did a relationship between the work and the kinetic energy, right? So how about here? How about when the body is rotating? So well, the equation, I'm going to write the equation, I'm not going to do the derivation. Well, it is half I omega squared F omega squared half I omega I squared. We have defined kinetic energy previously, so I'm just going to write the equation directly. So it's about this is the work done about a fixed axis. Okay, this is the work done about a fixed axis. All right. So now for the work done, if there is constant torque acting on it, theta 2 minus theta 1 or theta f minus theta I, both are same. Okay, in my words again. So here torque is equal to constant. Okay, must remember these equations. And now power. How do you relate power? So power is nothing but the rate at which the force acts on the body to produce displacement or to transfer some energy, right? So the rate at which the force transfers energy in one sense is called as power. So power can be written as d omega or dw by dt. Here w is either this or this. Okay, work. This work. So these are the three important formulas one should remember, right? So this gives you the power and so on. So in the next lecture, however, we shall discuss in detail about the angular momentum and the angular motions of the body of various shapes and sizes. Of course, what I've skipped in this lecture is definitely the formulas that you have, calculating the area in terms of angular, moment of inertia and radius and all. Honestly speaking, anyone can you can refer to the books for those formulas. I think it can be deduced from the equation that we've discovered. We've deduced the theorems. When applied to particular cases, you can do it. So I'll leave that to you. Okay. So again, thank you for watching, and goodbye for now.